Hello everyone. So the next concept is to find the horizontal displacement of the roller support at point A using unit load method. Okay, you can see this is again a frame, and it's a frame A, B, C, D, and at A there is a roller support, at D there is a hinge support, and 5 kilonewton external load is acting at A. Okay, so they've asked you to find only the horizontal displacement of the roller support. Find the horizontal displacement of the roller support at A of the frame. Take EI is equal to 8000 kilonewton meter square. Okay, so as usual, first what we'll do is first we'll find out the reactions of the original frame. So because it is only you have to find the horizontal displacement, so we'll find only the horizontal forces. We'll consider only the horizontal forces. So the horizontal forces are summation h is equal to 0. So in this, 5 kilonewton loading to the right side, and at D there is a hinge support. So hinge support has two reactions, vertical and horizontal. But we'll not consider the vertical because we are only interested to find the horizontal displacement. So this is RDH. Then, as usual, RDH plus 5 is equal to 0. So RDH is equal to minus 5. So RDH is equal to minus 5. Minus means it is acting to the left side. So we'll name this as P. That is nothing but 1 kilonewton. Okay. So then this is the original diagram. Next is we'll find the reaction due to point load. Okay. The same frame is again redrawn here, and instead of 5 kilonewton, we'll show it here as 1 kilonewton. We'll remove the external load, we'll replace the external load by 1 kilonewton. Again, why we are doing this is because according to the unit load method, whatever is the external load, that has to be replaced by 1 kilonewton. And wherever the displacement is asked, at that point we are going to replace the load. So here they've asked us to find the displacement at A. So at A, we are going to remove this 5 kilonewton load and add 1 kilonewton load. Okay, so now again RDH is minus 1. So minus means acting to the left side. So 1 kilonewton is showed it. Next, as usual, calculate the moment. Okay, so we'll cut every section and find the moment. So first, portion AB, BC, CD. Okay, and then portion of AB, origin is A. Origin in BC, origin is B, and in CD. Okay, now what we'll do here is, again, the choice is yours. You can take the origin either B or C. So in AB, I'll consider A. In BC, I'll consider C, and in CD, I'll consider D. Okay, so then limits. Limits is the distance 0 to 4, 0 to 3, 0 to 4, and let it go in the order only, always A, B, B, C, C, D. Okay. Then first mx is the moment due to the external load. So moment due to the external load is now given by, okay, we'll cut the section. We've shown here, we cut the section here. So in this portion, okay, 5 kilonewton is going anti-clockwise. So anti-clockwise negative. So it is minus 5 into x. Okay, next. When you cut this section here, okay, when you cut in the section BC, so it is now this external load 5. This is force into its perpendicular distance. So this is the perpendicular force into perpendicular distance. Again, this is going anti-clockwise. So minus 5 into 4 is 20. Next, RDH. Here RDH is also uh, positive here, 5 kilonewton. So it is now 5 into, this is going clockwise. So it is plus 5 into x. So 5 into x. Next, similarly, we'll calculate this. Okay. So 1 into x. So it is minus 1 into x. Next, 1 into perpendicular distance 4. Minus 1 into 4. Then plus 1 into x. Okay. And then once you find out this, EI is common throughout. So EI is common. Next, delta is equal to, again, as usual, put the formula 0 to integration from the limit 0 to L, capital mx into small mx into dx over EI. So again, mx into capital mx into small mx. put it here into dx. Next again this 20 into 4, then 5 into 1, 5x into 1x. Put the limits and then take out the common factor here. So this is 5 is a constant, 5 over ei, so it's x square. Then this is a constant number, okay, 80 over ei into 1 dx plus 5 into x square into dx. So then take the common terms here, take all the common terms and find out. And then when you go on solving this, so it is 1, take this common, 5 by 3 is 1.67 into 4 cube, then 80 over ei into 3, and then the final one is 4 cube over ei. So once you solve this, so it is 453.76. Now that you know the value of ei here, substitute the value. So we have got the ei value here as 8,000. So substitute here. So it is 453.76 divided by 8,000 is equal to 0.056 meter. So this is the horizontal displacement. So you have to write this as delta A H. So displacement at A, which is horizontal. Okay. So in the question they've asked only to find out the horizontal displacement. So you have to only calculate horizontal displacement. Okay. Okay, so the second type of problem where the unit load method is determine the horizontal displacement and slope at roller support D by unit load method. Okay, in this problem, they've asked you to find both horizontal displacement at D roller support as well as the slope. So you have to use both. Okay, you have to find both by unit load method. EI is constant throughout. Okay. Okay, as usual, first here they have given you two loads here now, 6 kiloton and 12 kiloton. But they've asked you to find displacement at D. So at D there is no load. Now at D, because there is no load, you have to artificially induce 1 kilonewton load. Why 1 kiloton? Because you're solving it by unit load method. Unit load method means wherever they asked you to find the slope or displacement, at that point you have to induce the load. Okay. All right. So first, as usual, find the reactions of the load. So reactions of the load, summation h is equal to 0, summation v is equal to 0, and momentum of A is equal to 0. Okay, so summation h is equal to 0, horizontal forces. So again, at A, there is hinge support, at A, there is a roller support. So at hinge support, two reactions. So RAH, RAV, RD. Okay, now to find the loads, so this is RAH. Okay, so RAH acting to the right side plus 6 kilonewton is equal to 0. So RH is minus 6. So RH I've shown here minus 6 kilonewton acting to the left side. Next, similarly, summation V is equal to 0. That is RAV plus RD is equal to 12. Okay, only one vertical force. Next, moment about A is equal to 0. This is RD into 4. RD is going anti-clockwise, so it is minus RD into 4 plus 12 into 2 plus 6. Again, 6 is going clockwise, so 6 into 3 is equal to 0. So then you'll find RD and RAB. Okay, RD and RD and RAB. Okay, after finding this, show it here. Next is to find the horizontal displacement. If you want to find horizontal displacement at D, so at D I'll put 1 kilonewton force. So again, 1 kilonewton, you just put it to the right side because it's being positive. So put it to the right. Now to stop this, now RH, calculate RH. So RH is, so RH right side, then plus 1 kilonewton to the right. So when you check this out, 1 kilonewton is acting to the right side. To stop this, RAH will be acting to the left side, equilibrium state. Okay, then everything remains there. Here 6 kilonewton, here 12 kilonewton. Only at D you will apply 1 kilonewton load because at D you have to find the displacement. Okay, then calculate the moment at XX. Okay, so first we go on cutting every section here. So A, EB, BF, FC, CD. Okay. So first let's start like this. So AE, origin is E. Again, this is your choice. You can take anything you want, either to the left or to the right. Okay, and then BE. In BE, we consider from B is the origin. Next in BF, PF, F is the origin. FC, C is the origin, and at D, D is the origin. Okay, so limits. First, AE 0 to 3, 0 to 2, 0 to 2, 0 to 2, and 0 to 5. Okay, let's start with this first MX. MX is capital MX here. So MX is in this portion first. I'm cutting the section here. So to the right side, check all the forces. To the right side of this, it's like opening the frame. So to the right side, consider all the forces. So to this, so in AE section, so 6 kilonewton is going clockwise. So it is 6x. Next, then there is one more load here, 12 into 2, this distance, because it reaches this line. Just 12 into 2, again clockwise. So 6x plus 24. Next, in BE portion, again in BE portion, so it is 12 into 2. Okay, this is 12 into 2. Then we'll also consider the forces here, that is 10.5. Okay, we have a loading here, this portion. So it is 10.5 into perpendicular distance, that is 4. 10.5 into 4. Okay, this into this. Okay, 12 into 2, then 10.5 into this. Okay, next, BF portion. In BF portion, so it is both 12 into x. So it is here 12 into x plus 10.5, so 10.5 into 2. Okay, all right. Next, in FC portion, FC, this portion, again to the right side. So it is 10.5 into x. And in CD portion, CD, so we're cutting the section length. So here in this section, there's no external load acting. And even the RD is acting along the line CD, so it is momentum. This is 0. Then we calculate mx, small mx. So again at this portion here, so it is 1. 1 is here. We'll consider to the, we're cutting the section here. Okay, it is 1 into total distance 3. 3. Okay, 3 minus x distance. Okay, next 1. Okay, 1 into total complete. We're cutting the section here. Complete distance is 5. So 5 minus x. We want only this distance here. So 1 into 5 minus x. Next, similarly, in BF portion, in BF, we cut the section here. It is 1 into perpendicular distance. 1 into 5. Next, similarly, in FC portion, again 1 into 5. Okay, and in last portion it is again, it is going anti-clockwise, so it is 1 into x minus 1 into x. So EI is common throughout. So once you get this, just use the limits, 0 to L, capital MX into small mx divided by EI into dx. So it is 1 over EI, put capital MX, small mx, again capital MX, small mx, again from the table only. Okay, put all the values. The last value, it is like 0 into 1 minus x, so it is 0 only. Alright, so it is 1 over EI. Okay, 1 over EI. Substitute all this. Simplify this first, then integrate all of these, and then find out all the values. So it is minus 204 over EI. So again, answer is negative here, and it is the deflection. It's a horizontal displacement, deflection and displacement at D. Okay, so once you find out this, next is you have to also find out the rotation. Now to find out the slope or rotation at D, you have to apply a unit moment. Okay, here at D there is absolutely no external force. So that point we have to add a unit load here. Okay, so this is the unit load. Unit load or the unit moment. Okay, this is called as a unit moment to find the slope. Then everything will be same as usual, summation H. Okay, to find out this, so first we'll find reaction RAV and RD. So summation H is equal to 0. There are no horizontal forces. Okay, so to only show this flow, then summation V is 0 and summation V is equal to 0. So it is RAV plus RD. is equal to 0. And then we have the third equation, that is moment about A is equal to 0. It is now RD into perpendicular distance 4. So RD is going anti-clockwise, so RD into perpendicular distance. Then 1 is again anti-clockwise, so minus 1 is equal to 0. So RD is equal to minus 1 by 4. And then we have this as, once you put this, substitute the value here, and you get RAV. RAV and RAV and RD. Either you can keep it in fraction or you can solve this. So you can simplify and keep it in decimal. Okay, then everything would be same again. A, EB, BF, FC, CD. Again, origin is same, like what you've done previously. Limits are same. Okay, so when you're finding moments will change. Okay, even the capital MX is same because external loading would be same. External loading would be same. So this part of the table remains same. So we're going to rewrite the same thing. Capital MX will be same. The only thing that changes here is small mx, because here because we're finding the slope, we're finding the moment, and we're applying only 1 kilonewton meter. So 1 indicates that is 1 unit load, 1 kilonewton meter. Okay, so as usual, we'll again find out this. Okay, now you can see here first thing. So it is in the first section, AE section. So we'll find out to the left side of this, there is a reaction here. So it is 1/4. Okay, so see here, RD. It is going in clockwise direction. So it is 1 by 4 into perpendicular distance 4. And there is 1 kilonewton force, 1 kilonewton meter force acting. So it is minus. It is 1/4 by 4 minus 1. So when you solve this, it becomes 0. Similarly, next EB in EB span. So check to the right side of forces. The right side of forces, again, it is 1/4 into its perpendicular distance clockwise minus 1. So again, it is 0, right? Next, in BF, okay, so this is now 1/4 into this perpendicular distance. So perpendicular distance here is x plus this distance 2. So it is x plus 2. Then again, this is going anti-clockwise minus 1. And in FC we are cutting section here. So it is 1/4 into x, okay, clockwise 1/4 kilonewton into x minus 1. Okay, and in CD, in the end, so in CD portion, this is anti-clockwise, so it is minus 1. Okay, then everything would be same. EI is same through. Then, okay, now you can see here, this into this, 0 into anything is 0, 0 into anything is 0. So only we'll be taking these two. So BF and FC. So this is BF. Check the limit 0 to 2, 0 to 2. Multiply this into this into this. Okay, 0 to 2, 0 to 2. All right, then 1 over EI, 0 to 2. Again, simplify this, multiply the brackets, open the brackets and multiply. Here also open brackets and multiply. Then go on solving this. Okay, so in the end, when you solve, so it is the answer you get it as minus 4 over EI. This is theta A. So theta A, rotation slope, is minus 4 over EI. So minus sign indicates it is anti-clockwise rotation. Okay, so the simple method of solving this unit load using unit load method is, one thing, wherever they've asked you to find the rotation or deflection, so at that point you have to remove all the loads and apply a unit load for deflection and a unit moment for slope. Okay, so with this we'll finish up with the unit load method. Thank you.